Can you see my screen, please?
Yeah, it is visible.
Excellent.
Emre, it's 2 p.m. Indian Standard Time. You may start your lecture actually.
Yes, thank you.
Thank you.
Warm greetings to everyone. Thank you very much for visiting this particular presentation. It will be about using agent technology in smart cyber-physical systems and in system development. The presentation will be divided into 4 blocks today. The first block is about the fundamentals of agent technology. What is a computational agent? This is the first question what I would like to clarify. And if I want to find the answer to this particular question, then I have to explain how does a computational agent look like? How does a computational agent operate? And what does a computational agent actually do? So in order to start answering these questions, we have to start out from the very concept of agent. An agent, and here I'm thinking of a software agent primarily, but it can be also a hardware agent or a hybrid agent. It is a computational entity which does something. And we can illustrate it with the following figure. Agent is embedded in an environment, and at first sight, it exists as a kind of self-contained black box. The details inside cannot be seen. But if we consider that the agent is related to the environment and has percepts related to the environment, and also does certain activities which are used to change the environment, then we can see that most probably the agent includes certain kind of detectors, certain kind of reasoning mechanism, and some sort of effector mechanism. As an example, which I will use today as a demonstrative example, just consider a restroom cleaning robot. This is definitely an agent because it is Please switch off the microphone. Colleagues, please switch off the microphone. I hear back a lot of noise. Thank you. So a restroom cleaning robot detects dirt, decides on the intervention, and executes the task, and then waits. It percepts dirt, if there is dirt, if the room to be cleaned empty or crowded, if there is a fault and the dirt is due to that, or it is possible to remove at all that sort of dirt. And the activities are like monitoring, locating where the dirt is, moving there where it is, removing the dirt, reporting that what it has done, and then returning to a kind of docking station and charge itself to be ready for the next operation. So this is the concept of the agent. And if we want to further discuss it, then I set the stage with the following statements. A computational agent is a multifunctional entity that is able to reason rationally and cognitively about the task it is supposed to execute. So there is a kind of smart behavior attached to it. to make its own decisions independently. So there is a given level of autonomy, and then to collaborate with other agents when necessary. So the agent has some sort of social aspect as well, and to perceive the context in which it operates and react to it appropriately. So there is a kind of reactive nature. And finally, to take action in order to achieve its goal. So it should be proactive and sometimes even define its own goals. An agent-based system, which is obviously a purposeful arrangement of a computational agent, it is a system where the agents are the main entities treated as first-class abstractions, and the same reasoning is followed from a programming point perspective. So in agent technology, we program agent and focus on the programming, on the implementation of agents rather than lower level structure. So it means that in agent oriented programming, the agents are objects. The agents are the entities which are treated, while in object-oriented programming languages, for instance, the objects are the entities what we are focusing on. So before going further, as I always used to do it, let's see how the agent technology and the sense of agent are explained by others. Obviously, here I will include a small video, and this video will show the technical details about the agent technology. So I hope you can see the video.
Your video is not visible. Hello, Imrit?
Hello?
Yeah, the video is not visible.
Sorry, please say again.
The video is not visible.
How comes?
You have to share it actually.
I restart it. How about now?
No.
No. Okay, then just a moment. I believe there is something again with the.
You stop sharing and share it again. Share the video again. Stop sharing that.
Yes. So I share it again.
And now the screen is coming. Yeah.
Yeah, and I hope that it comes now too.
Yeah, it is coming. Yeah, it is there.
Great. Thank you. I use this particular video for the purpose of showing
Sound is not on.
kind of consensus on what the agents are, and different research teams are talking about similar definitions and see the operation of the agent the similar way. But we can add a lot of things to this, and in fact, the rest of my presentation, I will talk about those sort of things, what we experience, what we believe important and not so frequently discussed on the internet. So the starting point is that an agent is a computational entity that functions continuously and autonomously in an environment in which other processes take place and other agents exist. So the agent should adapt to them. Colleagues, please switch off the microphone. Agent is representing an active part of the reality. Distinguishing characteristics are, for instance,
Your sound is not coming.
sorry, is there a problem again? Can you please switch off the microphone?
Well, all of you, please switch off your mics. There's a lot of disturbance coming today.
I very noisily listen.
Sandeep, I can't mute you also. Your mic is on actually.
My one.
Sandeep Bose. Can somebody take Sandeep Bose that his mic is on? He should switch on his mic.
So
continue, please continue. And sorry for disturbance.
No problem, I go further. Distinguishing characteristics are, for instance, that knowledge enables the smartness. There is a decision-making capability. There is some level of autonomy in operation, varying response behavior in different activities. There is the purpose of using multiple agents is modeling smart operation.
टेम्परेरी डॉक्यूमेंट पीडीएफ को डाउनलोड हो गया, डाउनलोड और कुछ नहीं हुआ, अभी देखता हूँ टेनेंसी लेटर कुछ ऐसा आ रहा है 1 2 3 4 5 करके पेजेस और
सॉरी आई
उसमें 32 पेजेस हैं तो
तो कहीं साइन करने का ऑप्शन नहीं आ रहा,
देख रहा हूँ बेटे, नीचे जा रहा हूँ, लेकिन ये तो डाउनलोड हुआ है, उनका अपलोड कैसे होगा?
डाउनलोड पापा नहीं करना है, अपने आप उस पे ऑप्शन आएगा। नहीं होगा पापा।
This log out in my document. नहीं.
Please let me know when can I continue.
इस पे भी डाउनलोड ही हो रहा है वो जाके।
फिर पीछे जाइए, एक बार पूरा पीछे जाइए और वो बस लिंक क्लिक कीजिए।
सॉरी, शिट। कौन सा वाला जो उनकी साइड पे था? हाँ वही है।
Hello, Professor Tandon. Can I continue, please?
Yeah, please. Sorry for some call came and I forget to switch off my mic. Please continue.
Yes, I'm sorry for that, but it was almost 8 minutes since okay, I go further with this. So we have various agent definitions. For instance, the one which says that computational agent is any type of independent component, software, model, individual, and so on, whose behavior can range from primitive reactive decision rules to complex adaptive intelligence. Adaptively behaving agents can in some sense learn from their environment and change their behavior in response. Agents should contain both base-level rules for behavior as well as high-level set of rules to change the rules. Essential characteristic is autonomous behavior, independent decision-making, and working according to that. That requires the agent to be active rather than purely passive. So agent may exhibit largely different behaviors, attributes. They can be reactive, proactive, adaptive, interactive, and so on and so on. I will discuss this issue later on in more detail. I also have to say that multiple classifications exist for the agent, and different taxonomies have already been proposed both for the agent behavior and the concrete manifestations of the agent. One classification of software agents, for instance, include collaborative software agent, mobile software agent, information network agent, interface agent, reactive agent, intelligent agent, plus, for instance, hybrid agent. So what I can tell you that if you go into the different fields of agent technologies, you might have completely different taxonomies, purpose-oriented taxonomies, and also completely different classifications. What is common, however, in the overwhelming majority of them, that agents individually assess the state or situation of the environment and make decisions based on the basis of their knowledge. So agents are primarily concerned with the state of the environment, and obviously they also have to consider their own state. When we want to taxonomize the agents, we actually have to see, first of all, what sort of dimensions are out there for the classification. Then we have to, first of all, consider the characteristics. Agent characteristics in a systematic way can be like proactive or reactive, can be collaborative or competitive, anchored or mobile, autonomous or interactive, adaptive or evolving, or for instance, smart, intelligent, whatever it means, and hybrid and composition. So these are the major dimensions of talking about the agent and characterizing the agent. I will use this model later on when I'm talking about the different manifestations of agent. So the common types of agents for cyber-physical systems are the following. Obviously, they are not mutually exclusive, so it doesn't mean that only one of them, one type can be considered. They can be considered collectively, and they can be even combined for specific purposes. The first one is the collaborative agent concept, which coordinate action to fulfill a common goal, but maintain their autonomy. Then we can talk about interface agents, which focus on learning more than on their autonomy. Then we can talk about itinerant agents, which are either transportable agents or reloadable agents, and both have the capability to migrate autonomously over computers and networks with their data intact, so they can take their data with them. And the last one, what I want to mention here, adaptive agents which change their behavior based on task, interaction, or the dynamic changes of the environment. We can talk about functional characteristics of agents, and the functional characteristics are such as like mobility. I mentioned this capability related to a particular category of the feature of the agent beforehand. So the mobility means that go with the system, the resource, the device, the group, swarm, the team, and go where sent. Then the next one is dealing with the environment. For instance, it means that having or building contextual awareness, searching and finding resources, and being in contact with nearby systems. Then interoperability, homogeneous heterogeneous peer system or device connection, communication, negotiation, collaboration, sharing intention, beliefs, and commitment. Commitment is actually decomposed into other aspects like intention, engagement, shared commitments when serving multiple systems in parallel, and balancing capability. Functional characteristic also is action planning, for instance, task definition, task ordering, sending the task to other agent. Then resource acquisition, for instance, planning, searching and finding, transport planning, resource control and management. And finally, reconfiguration is a last functional characteristic which has importance. For instance, we take things changing conditions, adapting operation or evolutionary responses. I have to tell you that in case of many agent implementation, the consideration of the time and the activity timing is also an issue, but it's also an issue with regards to the life cycle of an agent. Then the behavioral characteristics of agent is something what I want to talk about. With regards to its behavior, an agent can be interested, has the ability to recognize and distinguish the traits of other agents. It can be goal-directed, having goals to achieve, not necessarily objective to maximize with respect to its behavior. Foreseeing, then the agent has the ability to compare the outcome of its behavior with its goal. Autonomous, if an agent is autonomous, then it can function independently in its environment and in its dealings with other agents. Flexible, then the agent has the ability to learn and adapt its behavior based on experience and rely on some form of memory. And self-directed characteristics mean that it has and generates, the agent has and generates rules that modify its rule of behavior. Then the next important aspect is the social characteristics of agent. For instance, the agent can be cooperative. The agent is willing to help other agents to achieve their goals, potentially sacrificing achievement of its own. Competitive, an agent is, or the social behavior of an agent is competitive if it acts primarily to achieve its own goals and cooperation never occurs at the expense of its own goals. The independence as a social characteristics means that the agent acts on goals independently without cooperative either explicitly or through rule-based mechanisms. The agent behavior can be prioritized, which means that goal may have a prioritization structure that guides pursuit and cooperation. Then the social relations, so not just characteristics, but relations can also be identified with multiple agents. And one is commercialism, when one party gains from the relationship, but the other is not also not losing. Parasitism, when one party benefits from the relationship, the other suffers from it, but an equilibrium can be reached if the benefited accept the status quo. Cooperation means that both parties allocate resources and make common efforts to achieve optimum shared benefits. Then competition means that the parties compete for the same resources and help achieve a dynamic equilibrium in their objectives. Finally, predation means that only or that one party, one agent strives for limiting the number of other parties and pruning the weakest one for implicit benefit. Then we have to talk about the computational characteristics of agent. And the first one is identifier. It is a discrete individual with a set of characteristics and rules governing its behavior and the decision-making capabilities. In multi-agent systems, agents typically has name like human as well. The agents are discrete, which means that their operation and servicing has a boundary, and one can easily determine whether something is part of an agent, is not part of an agent, or is it a shared characteristic. Agent, from a computational point of view, can be self-contained, which means that the manifestation or the implementation of the agent contains or obtains all resources needed for the independent operation of the agent. Then the agent can be situated, which means that they exist in an environment with which it interacts along with other agents, and it is obviously in the background assume the context, understand the context building and context interfering capability. Then, from a computational point of view, the agent can be interactive, which means that they have protocols for interaction with other agents, such as for communication, and they also own the capability to respond to the environment. So then, until now, I didn't use the word smartness, but we are talking about agent in the context of smart cyber-physical systems. So what does then smartness mean in the context of agent? So agent may act on a single percept or on a sequence of percepts. The agent can adjust its operation strategy to the actual situation and or happening. This behavior is a kind of indicator of its operational smartness. The agent must respect external expectations, conditions, and restrictions. These are also the characteristics of some sort of smart behavior. In addition, the agent should take care of itself to maintain its readiness to proceed and to act. For instance, in our case, when we were talking about a public room cleaning robot, for instance, the charging is also a task to manage for this robot. And then it is other thing is that it is an agent design issue to determine how the agent will perceive, act, and sustain, obviously, but the agent may also be able to learn, adapt, and even evolve. So the next question to address is where to use agents inside our physical system. We can formulate a couple of reasons for it, so actually every one of them reflects a particular need. For instance, if there is a need for natural representation of virtual physical actors as agents with decisions and behaviors. If there is a need for comprehensive intellectualization of task execution, and it can be defined discretely with boundaries. If there is a need for behavior changing and adopting, learning and engaging, and dynamic strategic planning capabilities of the agent. If there is a need for handling dynamic relationship between actors, which are the agent in this particular case, which might be formed and dissolved in a volatile manner, the relationships obviously. Agents that have spatial component to their behavior and interaction, spatial agent. If there is a need for agent to learn from the past and to act as a predictor of the perceivable future. And finally, if there is a need for scaling up models and structurally change processes to arbitrary levels. So I mentioned that the agent operates in an environment. In fact, they together form what is called in the literature agent environment. And the agent environment has importance with regards to both specification of the agent and the task execution by the agent. The agent environment is both a design variable and an operational variable, and this is an important thing to consider when we start developing the agent and multi-agent system. More specifically, an environment can be fully observable. The sensors provide all necessary pieces of information about the environment. It can be partially observable, which means some aspects of the environment are not detectable or not knowable and predictable. And the environment can be static or dynamic, an environment can be episodic, sequential or disorder, and an environment can be discrete or continuous or hybrid. So you see that there are many characteristics of the environment which also to be taken into consideration when we specify the agent behavior and the smartness of the agent. So these together influence the specification of the task environment, I mean, those sort of tasks which the agent should accomplish in the particular physical environment. Then we need to talk about the characteristics of the agent environment, and unfortunately now I'm pressed by the time, and most probably I will not be able to go through all the descriptions, but I would like to mention at least that these sort of characteristics are something like observability, multiplicity, predictability, dynamism, episodicness, and continuity. And obviously, they can be formally defined and interpreted semantically that actually what does it mean with regards to the different measures which belong to the particular environment type. My slide will be with you. You can study it later. The next topic what I would like to bring upon is the planning of the behavior of the agent. The behavior means in this sense that how an agent reasons and the goals, what an agent aims to achieve, and their interoperation, how agents collaborate to solve a task, and these should be dynamically computed in context. The difficulty is in evaluating the performance and dependability. If there is a prior knowledge, it largely influences the performance together with the quality of the task planning and execution. So it means that the more specifically, more detailed the task planning that can be done by the agent and the sort of plan for the execution, how articulated, how detailed is, together with the a priori knowledge, which is what the agent has about the problem to solve, and also the method of solving the problem enhances the smartness of the agent through planning. So the smartness of an agent depends on its rationality of acting as well as on the measure of success at acting. The agent capability or legitimation of changing the environment is also an important thing because it plays a role actually in the agent development. Analysis of the task environment in the framework of performance environment sensors and actuators is recommended by the literature, actually a simultaneous analysis that we are talking about, and this is the so-called piece of framework. Specific appropriateness and performance indicators are specified for the properness of the planning of the agent behavior, and other measures can always be specified for particular applications which are different than the standard. Sorry for the delay, but it was due to the technical mishaps what we experienced beforehand. Let me close this block with an overview of the suggested literature. The first paper what I suggest is from Leitao and the co-author Smart Agent in Industrial Cyber Physical System. This is a paper which demonstrates the need and also the place or the role of smart agent in industrial context. Then I already mentioned the taxonomy, what was introduced by Nuana, and that is the paper. What I recommend to you is Software Agent, an overview. I apologize for this duplication. I don't know why it happened, but the next one is a comprehensive study on the different types of software agent. Here, something what you will hear in the next part of my presentation. And finally, a paper which is titled Smart Cyber Physical System of Systems using intelligent agent and multi-agent system is something that might be important for you. At this very moment, I do stop sharing. I come back to the mosaic, the screen images, and I would like to kindly ask you if anybody has comments or questions related to what I presented. I'm sorry for the disruption. That's the reason why we are in delay at this very moment. But I try to speed up in my speech, but actually I just could keep what I promised. Any question, any comment, please?
Anyone having any question or any comment?
Okay, the time goes. If there is no question, then I share the screen again. And I continue my presentation with the, oh, there is a chat, sorry, the chat comment here. No, it is not important, sorry for that. So let's go to the next block, which is about realization of agent for use in cyber physical system. So it will be a little bit more the practical side rather than the theoretical methodological overview, what I presented just a minute ago. So if we consider the realization of computational agents in cyber physical system, then there is a kind of thinking framework what we have to know and be aware of and even use, because several tools what we can use for agent development actually are centered around this particular conceptual model. This model called the belief, desire, intention model, and in the literature very often referred to as the BDI model. So the BDI model specifies a reasoning process that aids the decision making of selecting an appropriate action towards the achievement of some goal. Three captured mental attitudes are, which are actually reflected by the name: the belief, the knowledge that the agent believes about its environment or assumes about its environment, itself, and other agents. Then the desire states that the agent wants to achieve. The states obviously here related to the environment, but also related to the agent itself. And the intention, a sequence of steps towards the achievement of the desire. So we can say that the intention is the way of achieving the goals of the agent. So these mental attitudes respectively represent the information. The BDI is the most popular model of agency. It has been and continues to be used in many agent programming languages. For instance, the AgentSpeak-L is a language uses the abstraction proposed by BDI and uses it to interpret agent programs as whole closed logic programs. Before going further, I believe meaningful for us to cast light on how this belief, desire, intention workflow is actually organized. Here is a overview. So we have the input, we have the belief revision function, we have a storage place for the beliefs, we have a storage space for the desires, which are explicitly formulated and coded. We have intentions also in a basis. And then we have option generation functionality, we have filtering functionality, and we have a action selection functionality, which then produces the output. So as you can see here, the belief base, the desire base, and the intention base actually dynamically updated repositories which are needed for the operation of the agent. So if we want to deepen a little bit in the BDI workflow and we want to understand its sense, then we have to say that a major component of it is a belief revision function, which receives input information from the environment, for instance, directly from the sensor. And then the belief revision function is responsible for updating the belief base. This update can generate options that can become current desires. Many options can be generated based on the belief base and the intention base, and this calls for filtering. So these options, the belief options and the intention options, somehow together with the other operational alternative needs filtering. A filter is responsible for updating the intentions base, first of all, because the intention base is behind the actions and it is a kind of remote coordinator of the action. The filter takes into account its previous state and the current state of the belief base and the desire base. Finally, an intention is chosen to be carried out as an action by the agent. So this is how the inputs are actually connected to the operational output of the agent. So then the next question from a developer point of view, what types of agents can we implement for cyber-physical systems? And here we have to start out from the so-called general or common agent architecture. An agent is seen in a cyber-physical system as the lowest level node. And every node can be typified with this stereotype, namely that the agent, within the agent boundary, there are certain kind of agent functions implemented, which are dependent on the sensors and which are connected to the actuators. We have seen earlier in the overall definition what is happening. So the functional architectures to be considered can be something like simple reflex agent, model-based reflex agent, utility-driven model-based agent, goal-based agent, learning agent. And obviously we shouldn't forget about the special purpose agent, which are arbitrary, and for this reason I can cover them in my presentation later. But I will definitely focus on these 5 categories of the agent because they are all important. They provide certain functionality for smart cyber-physical systems. What is also important that each of the 5 ones what I indicated, they have so-called cognitive components which are based on some sort of use of sensors, the actuators, the decision maker. So let's look into this classification, what I briefly introduced already. So the practical agent can be grouped into these 5 primary classes, but obviously several other application-dependent classes can be implemented. They differ in the degree of the perceived intelligence and functional capability. For instance, a simple reflex agent acts only on the basis of the current percept as a condition action rule. The model-based reflex agent can handle a partially observable environment by a world view model. So this model completes the incomplete observation of the environment or incorrect observation of the environment. And this is why the model-based reflex agent can provide better operation and higher level of smartness than a simple reflex agent. Then we can talk about so-called goal-based agent, model-based agent, storing information regarding the desirable situation. Then we can talk about utility-based agents, which are actually updated versions, like the simple agent, model-based reflex agent. They are superior versions of the goal-based agent, and they can map the state's utility to a measuring function. So actually, they can control their progression on the path of solving the problem. Finally, the learning agents which are capable to update decision information by learned elements. So then let's look into possible implementation of these types. Let's start with the data-driven simple reflex agent. So this is the scheme. There is a sense verb state here, sense verb state, and then this agent category includes certain condition action rules which are controlling the actuator. So this type of agent are deterministic in a sense that they make direct mapping between the percept sequence and the selected action. And typically one percept triggers one action. Implementation challenge is not an issue. They are simple and for this reason easy to implement. The condition action rules need not take the form of an explicit sequence of branching code. Nevertheless, it should be expressed as a kind of conditional rule. Simple reflex agent can be realized as a feed-forward neural network, for instance, which doesn't undergo any further training. Obviously, there is a need here for validation of the reflexive responses because it is influencing the quality of the agent performance. So here, the major cognitive components, what we have to implement a kind of state of the sentence word, condition action rules, and that's all. Then the model-based reflex agent is also having a sense of the word state, but it also monitors the word evaluation because it can compare the information what is described in the model with the actual percepts, and then it can also have information about the action, the effect of the action, because the model is there, and based on the model, something can be concluded. But it works as in the previous type of agent with the condition action rule. So model-based reflex agent considers the environment they are embedded in, this environment may not be static over time, and they also consider that actions have consequence impact on the state of the environment. The model of the environment is not adaptive. There is one predefined model, and the agent is enforced to use this, otherwise the agent will be adaptive. The word evolution and the condition action mapping must be captured, and the pre-trained feed-forward neural network is also a proper implementation, practical implementation of this type of reflex agent. Here, the cognitive components are the model of the word evaluation, condition action rules, and a model of action effect. Utility-driven model-based agent can be described by the scheme. Here, there is instead of the direct rule activation, there is a utility maximization action before controlling the actuators. And on the input side, actually, the only difference is a utility evaluation, which is related to the representation of the word generated based on the sensorial or knowledge information which is available. So the utility-driven model-based agent augment the word evolution functionality with a metric, because otherwise it cannot make decisions. The utility-driven model-based agent enumerates the desirability of a given word state. The agent is able to select from a set of optimal, typically a Pareto type of optimal actions. These actions should lead to a more desirable word state or environment state. Everywhere the word should be substituted by the direct environment. Finding the locally optimal or globally optimum word state could be considered as a goal for the agent. And the utility-driven model-based agents differ from the true goal-based agent in that sense that they are in lack of explicit representation of such end states and the intermediate states, which are goal states with regards to the environment. Important again to mention the cognitive components which makes these agents smart. First of all, the model of word evaluation, the condition action rule, the model of action effect, and the utility function. These four are which are the cognitive smartness increasing elements of this particular model. And obviously, I mentioned the utility optimization, but this is just a reflection on the achieved performance. Then the next one is the goal-driven agent category. Here is the specification. So actually almost the same content, but there is a kind of goal aligning action executed here by the agent before operationalizing the actuator. So the goal-driven agents are implicit extension of the utility agent. They are equipped with the ability to label certain possible world states as desirable end states. And they are also able to identify the required intermediate states, sub-goals needed to reach those end states. And the goal-driven agent takes care of the selection of the sequence of actions required to reach those states which are planned. Cognitive components for goal-driven agents are the model of the word evolution, condition action rules, and model of action effect, as well as, like in the previous case, there is a kind of reflection here. This reflection comes from a goal aligning action functionality, which is also built into the agent. Then the last category is the learning agent. The learning agent shows a rather complex structure inside. So actually the information which is coming from the sensors is first of all critiqued, then it goes to the learning elements, and the learning elements is strong connection with the so-called performance element, and the learning element is connected to the problem generator, which is in turn related to the performance element, and then the performance element is actually controlling the actuators in this sense. So the learning agents are made up of a set of highly coupled subcomponents, as I just presented. Each plays a role in increasing the adaptability of the agent action selection behavior. It is needed in face of the dynamic or initially unknown environment, and obviously the changes in the environment should be learned, and what is learned and what is reasoned out, that should be the driver for the operation. The elements that I mentioned, namely the critique, the learning element, the problem generator, are a kind of auxiliary components, because the most important, most crucial elements in the the agent frame in this agent framework or even architecture is the performance element which encapsulates the complete functionality of the agent. So it takes also input on the efficiency of its selection from the critique part. It is indirectly related to that. And adjustments are made according to the learning elements, what the learning result in. The balance between the exploration and the exploitation is managed by a problem generator, which I already mentioned. The major cognitive components are here: the critique elements, the learning elements, the problem generator, and the performance element. So this was about one single agent so far. Now let's look into multi-agent systems. And multi-agent systems are natural endpoint of distributed system development patterns. Agents are characterized with concepts of rational agency and bounded rationality. When they work together in a multi-agent system, these are the fundamental characteristics what characterize the total of the agent behavior. Rational agency exhibits rationality in decision-making processes rather than through intelligence, whatever that might be. The bounded rationality means making the best or acceptable decision given the information available at a given time. Task-specific quality measures are to be defined for each problem domain because there is no universal measure for characterizing the behavior of the overall interactive behavior of multi-agents in a system. And then if we talk about system intelligence rather than smartness, then it is captured in an agent function which maps a sequence of observable percepts together with the state of the environment and any knowledge the agent has embedded within it on a priori basis onto the selection of an action from a final set of possibilities are considered. So talking about implementation of agent and multi-agent environments, then we have to talk about certain agent development platforms. And it is obviously needed because the development of multi-agent system really needs robustness, distribution, and fault tolerance. So explicitly, agent-oriented standards and software development frameworks have been developed. The most important for software-based agents is the communication standard of the IEEE code Foundation for Intelligent Physical Agents and acronym that's FIPA specification. An implementation neutral standard for interoperation of multi-agents in a system is the agent communication language specification. Since agents are more often than not implemented in the Java programming environment, Java has a special utility for agent and multi-agent development purposes, and it is called the Java Agent Development Environment, Java, which is a mature and well-established implementation of the Foundation for Intelligent Physical Agents. System portability across heterogeneous hardware is supported, for instance, by the Java Virtual Machine tool. So, a concrete implementation of the software tools is the multi-agent modeling toolkit, which helps designers in building rapid multi-agent-based applications. This is a kind of agent development environment where developers can have facilities like reusability and customized built-in agents. So actually, agents are stored in the multi-agent modeling toolkit, and the designer, according to their goal, can reuse them, can modify them, and activate them. The multi-agent modeling toolkit provides built-in agents which are developed using the Java agent development framework. It is possible to reduce the development time by using the Java agent development framework in the case of multi-agent based application because of this inherent prototyping capability and the management of design patterns. Nevertheless, there is a flexibility provided, a kind of level of openness with the multi-agent modeling toolkit because the designers can add or modify methods, behaviors according to their requirements. But it is very important that in this environment, in the GIAN environment, every change should be according to the foundation of intelligent physical agent specification, and the designer should keep it in mind. So then a other aspect of designing multi-agent system if they are holonic or not. And this topic, what I would like to present related to that is a holonic multi-agency and the holonic question. So many problem domains have self-similar properties. Examples of this problem may be recursively defined as smaller, lower-level instances of the same problem in their own right. And this is where the concept of the holon comes in, and the holon represents an entity which is simultaneously a part of something and a whole in and of itself. The nested hierarchy of the holons is considered as a conceptual framework, and actually this nested hierarchy is called as holarchy. Holonic multi-agent system built upon these ideas and realize holarchies of multi-agent systems. And these type of systems can be realized, for instance, based on the Arca platform. If you type in a search engine this as a search patterns, you will get information about it very easily. The Arca platform is a toolkit in itself for building highly concurrent, distributed, and resilient message-driven multi-agent applications. Here, I would like to mention the agent unified modeling language, because agent-based modeling is a crucial issue, and it is actually a specific approach which represents a system as a collection of agents and relationship between them. Here, I would like to feed back to the problems with the unified modeling language, which actually hasn't been developed for agent-based system development. It cannot express, therefore, the agent goals, generative functions, agent autonomy, multicasting, agent properties, and so on and so on. I believe the UML language is known, the unified modeling language is known most of you, and you know that it offers 9 types of function, 9 types of conceptual elements for representation of systems. These are mentioned here. However, this is a limitation because none of them is specific to agent and agent operation, and therefore a agent unified modeling language has been developed which tries to overcome these limitations of the UML. And this agent UML has an agent prototyping and repository facility. It offers transparent designing interface. It provides multi-agent based rapid application development. It also provides the designers the facility to edit agent code, which means to add the new features, new agent, or edit or delete existing behavior and agent. The AUML also provides designers with the facility to add new agent in the repository so the new element can be also stored. The designer can also generate Java code of the agent unified modeling language model by using the code generation function. So the multi-agent multitask interface includes the main panel, a panel to the agent unified modeling language, a so-called behavior panel, an agent panel, and the drawing panel. So here is a very brief overview of the multi-agent modeling toolkit, which uses the previous opportunity. Unfortunately, the time is very advanced, so I cannot elaborate on the details, but I believe the image is self-explanatory. So the complete functionality, what is provided just for the sake of comprehensiveness, agent repository, add new agent, edit, modify existing agent behavior, verify modified code agent interaction, then new agent introduction, converting the code generated in agent UML into Java code, and the code ensures agent interaction protocol, and input agent can be, for instance, visualized by the Petrinex code agent. And the outputs are also the agent specifications, and there is support to Java. This is the overview. This is what I could squeeze into the second book. And in the end, again, some suggested literature. First of all, Professor Rain's group produced a very meaningful paper on engineering multi-agent system, the state of affairs and the road ahead. I recommend to each of you to read or to have at least a deep look into this. Then Manzoor and the Zafar paper on multi-agent modeling toolkit I was mentioning. Here you can find other technical information about it. Then the third paper, Dimensions in Programming of Multi-Agent System, closely related to what we have discussed. Cardozo-Ferrando paper is a review of the agent-based programming for multi-agent system. This is also about the BDI, so I recommend you to read this paper. And the last one, what I suggest is multi-agent collaboration in open system. So this concludes the first presentation, and what I would like to put into your memory is the first block was dedicated to the fundamentals of smart agent technology. Then the second block dealt with the POSIX agent architectures, and it also cast light on the widely used agent implementation environment. So the next lecture is waiting for us. I stop sharing the screen here and come back to the communication interface. I wonder if you have any question, any comment. Was it useful? Was everything known? Did I confuse you? Did I mention something which is conflicting with your initial knowledge? Was it nonsense? I just try to provocate you to take a position.
So any question anyone has?
So seemingly I managed to confuse everybody so deep that actually even there is no space left for creating a comment or image.
Things are still settling inside them.
I believe, Pune, you have a task to do and to call out every faces who attended the first lecture and possibly will stay with us for the next one.
So
I'm done.
I'm sorry for the disturbance which created in the start of the lecture today. People including my mic was on and I was not noting that it's on. Anyway, if there's no question, kindly switch on your cameras. We'll have a photograph, group photograph. All ready? Good. Vivek, Mandoi, Rahul, Anand, your cameras are not switched on. Kindly switch on your cameras. Prashant, your camera is not focus properly. Now it's okay. The rooftop was coming. Okay, so everybody smile, please.
अब ठीक है
Okay, so with this we conclude the first lecture of the day, and although we are short of time, what time you want to give them 5 minutes break?
Yeah, approximately. Yeah, I will be back soon.
So it's 3:12 Indian time. We'll assemble after 8 minutes. 3:20 after
you.
8 minutes.
Wonderful. Thank you so much.
Okay, so we'll start 5 minutes late, but we'll finish on time. So please be there on time at 3:20. I'll come back in a minute.
Yes, please.
I think you may have.
Yes,
They're coming.
I start the presentation. Can you see the slides?
Yes, yes, I can.
Thank you so much. And the recording is on.
Recording is also on.
Thank you. Then I start really.
Yeah, you can start now, I think.
Thank you.
Thank
The second lecture today is about model-based design and component-based realization. This twin topic actually lead us to a jungle. It is very comprehensive and multifaceted domain of this course. For this reason, I will not be able to discuss this exhaustively even on the concept level, but I would like to present a couple of important things what we have to consider as cyber-physical system integrators, because that's the point here. So the first block will be about market-oriented and model-based development of cyber-physical systems. The reason behind emphasizing the market-orientedness is that nowadays a lot of prototype cyber-physical system nodes are set up in laboratories, and certain nodes started to cooperate over the boundaries of the countries here in Europe in order to gain more experiences with cyber-physical systems. But whenever a system development is initiated, it should be considered as an innovation project. And the innovation has three aspects to cover. One, to make a decision on the desirability. So, is it really needed? Is it really something which, namely the planned cyber-physical system, is something which addresses certain social and human concerns? The second thing is viability. If we invest that large amount of knowledge and effort into the development of a cyber-physical system, will it return the investment? So there are business and market concerns which are to be taken into consideration. And the third one is actually the feasibility, the technological and production concerns. What is important here to see that these concerns not just interplay, but they beg for a balanced comprehension. So, for instance, the technology cannot get preference in the cyber-physical system innovation with respect to, let's say, the business or the social aspect. There is a reasoning model which actually tries to clarify the interdependencies between the various actors which influence the cyber-physical system innovation. On one hand, there is the societal demand, and the other side are the technological affordances. What is needed and what can be, what is possible. Cyber-physical system development needs a kind of streaming of the recognized probabilities and requirements into the domain of technology affordances, and then the possible functionalities and commercial feasibility should be streamed towards the decision making from the side of the societal demand. And then obviously, if these receive the mentioned balanced comprehension, in that case, we can end up with certain marketable offerings. This marketable offerings can be actually a dominantly hardware system. It can be a software system. It can be service system, and it can be something which offers experience. So when we consider the recognized probabilities and requirements, then enablers are needed, which are through the technological affordances are creating a short-term loop here. And if we consider the possible functionalities and commercial feasibility, then we have to consider the market values. And this is an other loop here. So this is the complexity what we have to consider. And then obviously consideration of the recognized probabilities and requirements are typically influenced by the scientific principles. How can we decompose the problem complexity, and how can we find solution for the part problem? Why the other side we have a much softer critique, which is coming from the acceptance possibilities by humans and in general the influence of the human factor. So this is the starting point. This is the framework in which we have to consider. And then we also have to consider that system science and system thinking tells us that we might have two alternative views with regards to system development. And one of them is the system level view, and the other is the so-called component level view. What is interesting that they resemble each other. On the other hand, their strategic approach is different because, for instance, a system level thinking starts from a assumed complexity and then defines different aspects to see. It deals with the interaction of the aspects, and then it defines the constituents of the system. While a component level view starts out from the possible component. It investigates the interrelationship, the possible interrelationship, or the necessary interrelationships between the components, and then it frames them, it puts them into a system, and then study the system from the different aspects. So please see the same model, but the ordering, the thinking process is completely different here. So the system level view can be characterized by the holism, synergy, compositionality, ampliativeness, self-adaptability, and interoperation, while the component level view can be characterized by reductionism, functionalism, composability, additivity, task adaptability, and the interaction. Completely different approaches. Please remember this model because in the second part of my presentation, which when I will talk about composability and compositionality issues, this comes out. So if we talk about system integration, and I used mission model, which was published almost 25 years ago, but still valid as a kind of highest level conceptual model, it's identified 4 core elements of the strategy. So if we want to get to an integrated system, then first of all, we have to provide functional interoperability. We have to take care of semantic consistency. We have to ensure structural interconnectivity, and we have to take care of forming convergent workflow. So these are the 4 highest level, somewhat abstract requirements that we have to decompose into concrete requirements at the time of proposing the system innovation. And then obviously functional interoperability has to do with the system modules and components together. They have to implement the internet operations. Then the workflows are to be defined in a way that they are really integrated from technological, business, human, and social perspective. Then the semantic consistency means that the system operations related to data and knowledge are interpreted with the same meaning and in the same context. And then The structural interconnectivity means that the system modules components are purposefully interacting with each other. So far, so good. But if we just consider the current vocabulary of system development, we can find two conflicting terms. One of them is model-based engineering, which is the integrated use of models to define the system technical baseline across the full life cycle and all disciplines. And it is based on models which can be domain, meta, or even mega models, which are iterative definitions of the system. And this contrasts model-based system engineering. So model-based engineering and model-based system engineering are somewhat different because model-based system engineering is a special type of descriptive modeling used to create and analyze system engineering information across the life cycle. Why is it important? Because when you make a search for related papers, it is not all the same if you use model-based engineering as a keyword or if you use model-based system engineering as a keyword. So model-based system engineering, in model-based system engineering, a model is a representation of the system at some level of abstraction, and abstractions play an important role here as we discuss later on. And as I mentioned beforehand, the model is seen as a kind of iterative definition for all system engineering information. Let's look into model-based engineering. What is it all about? Instead of a verbal description, I try to visualize the major element, which is, as my previous slides imply, actually starts with the emergence of the need for a cyber-physical innovation, and this need reach the developers. Then, based on the need, there is a requirement analysis on multiple levels and from multiple perspectives executed, which is followed by a functional definition. This called, because this interaction between the requirement analysis and the functional definition is called the specification loop. After the functional specification, there is a kind of architectural configuration action done, and this is often referred to as the architecting loop. After that, there is a phase which is about definition of the operations based on the models, mathematical representation, and so on, and this is called the behavioral loop. So seemingly, it looks like a waterfall model, but it would be nonsense to execute it in a linear way because model-based engineering actually lends itself to a kind of self-enhancement. What it means more concretely is that, for instance, when the system control and simulation is done, you can connect to each previous stages. You may change the requirements, you may change the functional definition specification, you may change the architectural configuration, even the operational scenario. And this is what is called in the process of, or in the scenario of model-based engineering, a control loop. Now, on the other hand, if you consider that you have a virtual system and you don't know exactly what it does and how it does the things what it does, then you need to go into system verification and validation. And this is also connected to this is connected specifically to the operational scenarios as well as the requirements. And this is called the verification loop. So this is what, for me, model-based engineering means, and there are and the overwhelming majority of authors in the related literature use also this sort of conceptualization. So here, what is interesting, that the need comes in, and then the system specification goes out, and then it also means that there is a process which is coming in, a real life process, which is changed by the developed cyber-physical system, and there is a output process which reflects all the effect of the developed cyber-physical system. Now, if we want to deal with model-based system engineering, then you see the difference based on this figure, what I present. So it actually starts with studying real-life systems and based on a certain kind of systems, system architecture, system prototype, system stereotypes I identify. So what the interest is that the real-life systems are naturally occurring, artificially created representations can never be imagined, and typically a kind of hybrid realization, which means that the natural and the human production capabilities are taken into consideration. Then the process goes further with creating a kind of correspondence relationship with the conceptual system. So the system appear here in a conceptual domain. And then these are called the abstracted system, while whereas previously we were talking about recognized system. So this is what is typically modeled, a abstracted system, what is modeled. And then the process goes further because, oh, sorry, I have to mention here that, for instance, when we are talking about models, it has aspects like sharing human mental models, defining formal models, and displaying digital models, and sharing informational models. And then the process goes further, and then we create a kind of feasibility relationship with the systems which are implemented. This is the real system, and these are the engineered systems. So actually, this, as you can see here, this correspondence relationship expressed if you can capture, if you can at all conceptualize and model that particular system, what is inside, what we are aiming at, why the other branch is investigating the feasibility relationship. So these are, I believe, transparent figures to see the difference between model-based engineering and model-based system engineering. So let's talk about model-based design because this is methodologically a important field of knowledge. First of all, models represent requirement, architecture, implementation, development, depending on the concerns as it is implied by the previous images that I showed to you. Models are describing by using modeling languages which include abstract syntax, concrete syntax, and semantics. The abstract syntax in the modeling language typically describes the concept of the language and their composition to create a model. A concrete syntax, on the other hand, is a textual or graphical visual notation used to describe a model. And then the semantics component employ the meaning, the interpretation of the model, which is expressible in the corresponding language. So semantic is or can be defined either formally by using mathematical notations or informally using natural language. And these obviously not playing equal role inside of physical system development because we prefer to use representations which are formal based on mathematical notions, but sometimes we cannot get so far due to the intuitive nature of the information set that we want to represent. When we are talking about model-based design, we have to be aware of the fact that actually there are development time models and there are runtime models. Let's look into these two things. Development time models are which are used by the designers or the developers at the time when they conceptualize the system and when they go into the detailed specification of the system. A development time model starts from a abstract model which describes the system requirement. The requirements are systematically transformed and refined through architecture, design, implementation, and deployment models. The development time models bridge the problem space, the application domain, and the expectations of the application domain, and the solution space, the domain of implementation, the third space actually, what the designer can move up and down. It is not sufficient to realize complex systems relying exclusively on development models, on development time models. So the runtime models often have to be also considered. The reason are the changing conditions in the system environment and insufficient information at the design time. So we cannot squeeze all necessary pieces of information into a development time model because of the simple fact that it is too much and we cannot foresee everything. So that's the creates the need for runtime models and the use of runtime model in order to complete the insufficient information which is conveyed by the development time models with the information that can be accessed or acquisited by runtime models. And this raises the need for modeling self-adaptive systems which are constantly adapting to the environment or to their self. And it needs a kind of extension of the model with an engineering to run time with models, and this is what is very popular in the literature at this very moment, to use models at runtime. This is a particular approach, methodological approach to develop models and models runtime, and these are simply referred to as runtime models. So runtime models are causally connected representation of the system structure, behavior, and goal. The causality is important because with this runtime model, you want to reason and even you want to learn new situations. A runtime model is causally connected to a running system, so it assumes that the system is operating throughout in life cycle, and if the model is changed automatically or whatever way, it influences the operation of the running system and vice versa, because if the running system changes, then the model is supposed to adapt to that. So this can be achieved through the causal connections which are established in a bi-directional manner. It comes from the above statement, what I mentioned. So the connection of the model with the running system. The runtime model is an exact reflection of the system at all times, kept up to date based on the data from the running system, and obviously here the sensors and sensor networks play a crucial role to provide the momentary information for the modeling purpose. The primary advantage of runtime model is that they enable automatic monitoring and analysis of the systems while it is running. Not only one runtime model, but actually multiple runtime models can be used in a system. They are referred to as connected runtime models, and they can also be used to effectuate change in a system of systems. So multiple interconnected systems can be developed based on runtime models. When multiple systems are involved, this is typically referred to as the runtime dynamic control over system. On a model level, a particular change should have equivalent change in the running system and vice versa. but the change, first of all, should be negotiated on system level and then downloaded to the constituents of the system. This is how runtime models are used. When we are talking about development time models and runtime models, you can see that development time models are typically considered as static, while runtime models are considered as dynamic. So static models usually created during the system development time, and you cannot live with these models just with static models, because the smart system is really influenced by the dynamism of the environment, and it has to be considered even on a kind of near zero time or real time basis. So keeping the system models alive at runtime results in the need for dynamic models. So I mentioned it, a dedicated runtime model, or this special implementation of the runtime models, which is represented by the models at runtime framework. It is trivial from what I said earlier that the runtime models are continuously updated with information and events that are occurring during the execution. The term event is very important because most of the system is event-based control, and events can be managed as discrete entities in the process of the operation of the system, as opposed to signals which are obviously continuous analogous quantities and values, but more complicated to manage by digital system because you have to sample them. So the continuous update assumes supporting reasoning, taking corrective actions in the model, and potentially changing the decision-making behavior of the systems at runtime. A runtime model can be specified based on final state machine formalism, for instance, based on the structure of labor transition system. And then the last note here is that dealing with behavioral model demands a solid mathematical background of the software engineers and the systems engineers in general. In order to support their work, there are so-called modeling languages. And the modeling language, as I earlier mentioned, typically consists of abstract syntax, concrete syntax, and semantics. Since the time is running very fast, I would like to step over a couple of notes here, because later on you can study it based on the presentation material, but to end up with the reintroduction of the unified modeling language, because earlier I was talking about it, that it is not completely sufficient for the agent-based modeling, but I may assume that not everybody is an expert in the use of unified modeling language, and therefore let me tell a couple of words about it. For instance, that it is a kind of historical development introduced first in 1997 by the Object Management Group, and this has become a standard language for specifying the artifacts of software systems. Nowadays, many attempts are out there to use UML for defining cyber-physical systems, but obviously limitations are found, and for this reason new initiatives are also taken to add more expressive cyber-physical system modeling languages like the Ptolemy and similar approaches. Unified modeling language can be applied modeling physical process flow, which is important from the perspective of cyber-physical systems. UML offers functions for visualizing, constructing, and documenting information flow. UML eventually is a visual pictorial modeling language used to make blueprints of information processing by software. And UML differs from programming languages, so actually it is a representational specification of formalism rather than a concrete programming language like C++, MATLAB, Python, Java, or COBOL, and others. So if we look into what UML can offer for cyber-physical system development, then we can capture its nature, that it provides a conceptual model of entities, attributes, and their real-time relationships, their interactions can be captured with it. The fundamental concept for the UML is based on the building blocks, the connecting rules, the common mechanisms, and the ULM, just for the reason that it has been proposed at the end of the 90s, it's strongly rely on the object-oriented thinking, and it means that a object encapsulates the data and all the controlling methods. The data represents the state of the object, and the object is described by a set of class and forms as a particular hierarchy. And important element is, and the useful element, that this mentioned hierarchy of real-world system can show inheritances. So it means that higher level objects can transfer their methods to, and also data to, lower level implementations, and in some cases it's through bottom up. The classes are flexible from that point of view, that they can be associated in various ways, and this gives a kind of flexibility for the design and for the representation. Object-oriented resources for UML models are the objects that I already elaborated shortly on. They represent an entity as a basic building block. There are classes, which is a kind of blueprint or concept of an object. We have abstractions, which represent the behavior of a real-world entity. We have the inheritance I just mentioned. It is a kind of mechanism that makes new classes from existing ones and inherent the data structure related or the processing method to the derived entities. Encapsulation is also important element, computational element of object-oriented thinking, because every object is actually a closed entity, and it has a mechanism to bind data together and hide them, as well as methods, for instance, which are local from the outside world. The last thing is what I believe important to mention is polymorphism, which means that that the mechanisms implemented by object-oriented programming can be very different, and they can coexist in different forms. There is something what is really a new topic, but I would like to share it with you, and this is about parafunctional capabilities. I don't know if you have ever heard this concept of parafunctional capabilities. Most probably you know what sort of functional capabilities cyber-physical systems you have, because in one of the lectures I was discussing functional capabilities, and actually I presented a comprehensive model which discussed the functional capabilities of models. So para-functional capabilities are what is behind them and behind these sort of operational functions. And actually these are not about what to function, but more about how to function. Parafunctional capabilities are a new domain of research in cyber-physical systems, related to cyber-physical systems. And I would like to encourage you to take it up, because if you do research with regards to capturing parafunctional capabilities in cyber-physical systems, for instance, emotion or attention or secrecy or these sort of things, definitely you can contribute to the cyber-physical system development. I have to emphasize the yes, parafunctional capabilities are completely different than the auxiliary operations, and as I separated them from the parafunctional capabilities, they need different treatment. So there are many understanding and implementation issues related to parafunctional capabilities, which are, as I said, important for next generation cyber-physical system, but we don't know enough about it, and still research is in an early stage. In your research, you can interpret parafunctional capabilities as background or accompanying operations for cyber-physical system. However, that you cannot be taken as habitual or abnormal. They are regular operations, but different than the main operational functions and of cyber-physical system. You do pioneering work because the current literature is very much limited on this. On the other hand, there is a important need for it. Here on this slide, since the time is running fast again, there are some research goals that we might address. In the end of this block, let me suggest a couple of further studies. For instance, Nexon and Caruso's paper on physical system modeling with Modelica is a early introduction and gives a kind of deep overview how to capture physical systems in models. Then the next paper is about comparison of dynamic system modeling methods. It provides a kind of basis. Then Gu and Tang paper, metasynthesis approach to complex system modeling is might be useful for many of you. Then a multi-author paper is what I mentioned here, cyber-physical modeling and simulation. And the last one is from the laboratory of Professor Edward Lee, and this model-based design methodology for cyber-physical system. That's all, and at this very moment I stop sharing. Actually, I must tell you frankly that the delays are aggregating, and at this very moment, I don't know if we have sufficient time for taking questions, but I kindly leave it on the decision of the chairman. Shall we go further, or can we stop here for a moment to take questions? I believe this silence, what I experience here, is the indication that the best is just to go further and to summarize the last part. So again, I'm sharing my content, and please shout or send me a note in the chat if you are not able to see my slide, but I hope you are able to see. So the last part is about component-based realization of cyber-physical system. The first part was about the development, innovation, design issues, and it will be more about the realization. But on the same conceptual level, because due to the extreme broadness of this topic, I cannot discuss everything. Typically, the cyber physical system implementation is scenario based. It is related to or relying on a set of scenario specification. This is scenario-based specification is a kind of alternative of the workflow-based specification for system implementation. And the goal is with this is to achieve easy understanding and manipulation due to their high level of abstraction, or contrary to the high level abstraction that we have to encounter. Scenarios are represented either textually as narrative description or graphically using varied notation. Most important graphical formalism for scenario-based implementations are FATINEX, the already mentioned UML. UML has special resources which are the UML sequence diagram, what you can use for scenario-based specification of implementation. There are also message sequence charts or live sequence charts or model sequence diagrams, and as well as use case maps, what you can use for this particular problem. Don't forget that systems can be very different, and their relationship, that their operational relationship with time is something what gives a basic consideration for system modeling. According to their relationship to time, systems can be continuous time system when the input and output signals are continuous time signals, for instance, in linear time invariant dynamic systems. And then you can produce an idealized model of the physical device by describing it with the theory of differential equation. We can talk about discrete time systems, which are working with discrete time signals by taking it as input, and based on that they generate discrete time signals as output. Discrete time systems can be static or dynamic, causal or non-causal, time invariant and time variant, and linear or non-linear, or stable and unstable. Then finally, the third basic concept that is used often in system modeling is the final state machines, which are abstract mathematical models of computation that can be in exactly one of the final number of the states at any time. Final state machine can change from one state to another in response to some input that is called the transition. Many of the representation languages, modeling languages, for instance, the Pratt-Net-based representation is operating with the concept of nodes and transitions within. There is a logic of system development, which is often illustrated by the so-called V model. It includes a development cycle, ideation, specification of the system requirements, specification of the subsystem requirements, specification of the component, and then the detailed design of the component and their interfaces of that. Then there is a kind of implementation stage in which acquisition, making, coding, building, and virtual prototyping of the system components and subsystems are done. And then the system realization is going from the bottom to the top, while the development started from the top. So it was a kind of a done procedure. The realization is conceptualized by the V model as a bottom-up procedure, and first it starts with the component level interfacing, then the subsystem level integration and interfacing, then the subsystem verification and validation, and then the system level integration and verification, validation, and the real life operation. There are interrelationships between the same levels, but obviously the procedure is procedure always follows the three shapes. Here I would like to mention that that actually the upper part or the let me say the first part of the V model represents what we discussed as model-based development, and the other part, this part, is often referred to as the component-based realization. I was talking about components, but I believe components are very much familiar concept for all of you. It doesn't matter what complexity level they appear, if they are one logical unit, there are treated as components like processors and so on and so on. But don't forget that components can be not only physical parts, but also software parts or even knowledge parts, knowledge chunks. So this is what I mentioned here, but at this very moment, for instance, the top cyberware component management, which includes data chunking, knowledge chunking, awareness representations, and so on and so on, is not really advanced. What I intended to tell to you related to the component interpretation, that the utility of component-based system design in the case of next generation cyber physical systems is questioned. And the very reason is that the components are assumed as discrete element, discrete entities, and certain kind of cyber physical systems overpass it, and they need different concepts. So here some additional ideas about components. For instance, I mentioned that there can be even subsystems, but in working with this sort of complexity, we typically use abstractions which describe the properties of the components relevant to their composition, transfer functions, user interfaces. But obviously, this abstraction ignore the implementation details. The component is the superposition of structural models, a behavioral model, and an interaction model. Components should have rigorous interface specifications that are rich enough to cover all phases of the life cycle. System design is obtained by assembling strongly encapsulated components according to these specifications. As I mentioned earlier, the whole component and strictly component-oriented thinking seems to be somewhat obsolete with a view to the smart cyber physical systems, where a synergy, a system-level synergy is created, for instance, by the knowledge that is aggregated in the system. There are some characteristics which are requested from the components. For instance, they should be standardized, they have to be independent, they have to be composable, they have to be deployable, and they should be documented. Component-based design has a particular logical framework in which various activities are happening. For instance, first of all, domain analysis, then system functional specification, as my earlier circular process model indicated it, the system architecture specification, and the repository of the components are activated. Then there is a specification of the components according to the V model. If you want to have the components manifested, then you search for the component in your own inventory, or for instance on the internet. Then when you have candidate components, then you use them directly if they fulfill the requirements, or you adopt them, and when it has been done, you assess the components in themselves for their functionality and in the context of the whole system or subsystem. This is what is implied as a kind of thinking framework by the V model. Component-based design involves creation, integration, and reuse of hardware, software, and knowledge-ware components, as I mentioned. However, it doesn't describe or prescribe a particular architecture. The architecture is created as a set of interrelated, functionally interrelated components. And I mentioned the reusability of the components, which is a economic issue as well as a kind of productivity issue. And different situation exists with regards to hardware parts and software parts. Hardware parts are typically adaptable physical modules. Software parts can be software framework, objects, architectures, and design patterns. Unfortunately, cyber parts are representing much novel concepts. For instance, let's say a information construct, which is one representative of entities in the cyber world. Further resources needed to bring them to the level when they really can be managed on component level, and a meaningful effort is obviously the ontology development for this purpose. In general, a main issue is handling emergent properties and behavior. Architecting is playing an important central role in the system formation, and these are the aspects, some soft and some harder aspects to be taken into consideration. So I mentioned that the traditional component-based design principles are not always applicable to systems, and especially there are certain limitations with modern smart knowledge integrated systems. And my explanation accompanying this phenomenon is that composition is a kind of generic design and implementation principle in many engineering disciplines. There are two key criteria for deciding on the applicability of component-based design in a field. For instance, if you have really a composable situation or you have a composability situation. Here, composability expresses that component properties are not changing as a result of their interaction with the other components within a system. So you can compose objects together if this condition is stands. So composability means that you have all the components, and then you can integrate them into the system. And what the system does is actually the total, the added operation of the component. But this is what I wrote here, a measure of the degree to which components can be assembled in various combinations to satisfy specific user requirements. This is what composability composability is expressed. But then component-based design can or should be extended to the domain where compositionality appears. Compositionality, for instance, is trivial for knowledge integrated systems and data intensive system, that this cyberware is actually creating a holistic unit, and it cannot be decomposed into parts. So it is again the decompositional technique. What is interesting in the case of a compositionality requirement is that the synaptic system upfront cannot be decomposed into discrete set of components. So you cannot separate the components from each other because, for instance, they are interrelated based on the necessity that they should jointly produce a particular piece of knowledge. Compositionality as an important term determines if synergetic system level properties can be established by local properties of the component. The lack of compositionality causes that systems do not behave well outside a small operational envelope. That is a consequence of the dependence of the components on each other. Model-based design helps manage complexity, increases dependability, decreases time to market, and optimizes cost, but actually it is very vaguely addresses the compositionality issue. We have to take away that a CPS is compositional if it produces emergent behavior, and these emergent behavior may be derived from the behavior of all its components together, from the interaction of the components. So we have a system compositionality challenge, which is opposing the component level composition of the systems that I mentioned, and component level system architecting implies a bottom-up reasoning, while the compositional type of system developing implies a kind of top-down reasoning. So everything should be designed derived from the synergistic system. This is why we differentiate composable architecting and compositional architecting. In order to see it with the mind, I put here that the composable architecture produces a part-induced wall, while the compositional architecting produce a whole implied part. With compositionality, I would like to mention that it can be functional, it can be architectural or behavioral, and the predictive compositionality. And in order to support compositionality-based architecting, there was a so-called contract-based design methodology proposed, which substitute the interface concept in the composition-based system development with contracts between the potential entities, and it is based on output guarantees and input assumptions. So here you can see a image about what is the role in context. I believe the image is self-explanatory, and you can see it. Contract-based compositional design is what I specified in one of these last slides, and I have to conclude because the time is very advanced. I suggest as a literature for to consider a paper titled Modeling Cyber-Physical Systems with Semantic Agents, very comprehensive paper. Then Professor Stepanovic and the colleagues presented the open meta concept, which is a model and component-based design tool chain for cyber-physical systems. The next proposal for me is the model interface theory for component-based component-based, don't forget, design, and the next one is beyond software product line, the variability modeling in cyber-physical system. This is also important, I believe, and the review of cyber-physical system 5 components architecture, the 5C architecture. We have discussed it last week for manufacturing based on standards. So I have to stop now. We have some delays still, but at least I kept the time on my side and I'm happy of it. Here is a brief summary, what you heard and what your takeaway can be. This lecture was about model-based design and component-based realization. I made a kind of demarcation line between the two, but on the other hand, on my presentation, you have seen that they are in effect inseparable because they have mutual dependencies out there. The first block of my presentation summarized the market-oriented and model-based development of cyber-physical systems. The second block discussed the main principles of component-based realization of cyber-physical systems. Please tune for the follow-up in the afternoon for you and also for the last presentation day tomorrow. And this concludes my presentation. I stop here and I'm just looking at the image board. I don't know if there is any comment, any question, anything what is important to discuss, or there are other more important things to do.
Any question or any comment from your side?
We can conclude then that it was a very questionless day today, and most probably I will contact the Meteorological Institute if there will be or not tomorrow a kind of question shower. And just to compensate for the missing questions today. It was a joke, obviously.
Okay, then if no question, again, please switch on your cameras so that we can have a quick photograph. Swati, Vivek, Sanjay, Srinivas, Keshav, Sandeep.
This is the most important action in the whole presentation. See,
Yeah, Vivek, are you there? Vijay, you have to switch on your camera. Yeah.
I have a question, Pune. May I?
Yeah. Please.
Did you think about our farewell party tomorrow? Have you made some sort of arrangement for a farewell party? Because when it is on site, we always have a farewell party after a course like this. So how shall we do it online?
So it will be virtual.
This is a task for you for tonight.
Okay, then. So we'll reassemble at 4:30. Mr. Gupta, you will be taking 4:30. You have to switch on your camera mic, please.
So thank you for the attention to my lecture today. I promise to make you tomorrow also get bored, with my last presentation, but maybe later on in time you will find it important and you revisit all the things. Thank you so much for the attention.
Thank you, Professor Emre. Thank you very much for.
See you. Bye-bye for now.
Bye. Bye. See you tomorrow. Tomorrow
See you
morning,
in the regular time. Bye-bye.
10:30. Yeah.
Bye-bye.
Vijay will be starting at 4:30.
So, in 5-6 minutes, only 6 minutes are left.
Yeah. Fine. So I'll stop recording now. I forgot to stop recording.
Intensive.
Another 6 minutes will start.
Yeah.
Okay. Thank you. Vijay, are you there?
Yes, Sunil.
Should we start?
Yeah, we. So I hope I am audible. So today what we are trying to do, we had already seen various aspects of the cyber physical systems. Professor Emre has discussed them in detail. In last 3 days main practice session, we had seen the software aspect, so how to simulate the things, some on MATLAB or using the Python, or how the convolutional neural networks can be done. So we had already discussed the software part. Because of the limited time, we cannot discuss it in the full, but the initial knowledge we have tried to dissipate to you. And if you are having any questions, anything, you can just ask us, you can write to us, we will try to reply you. Today, what we are doing is that we have taken the simulations, but how really the cyber physical systems work in the real system, or how we can transfer. Basically, if we see the cyber physical system, what they are doing is basically we are having the device or field lever from which the information is collected. This information is then processed, maybe in the nearby computer or nearby computation facility, and or through the network it will be transferred, and then it is transferred to the cloud, where the big data analytics or other techniques can be used, and then it can be shared with the other users. But in real life, how do we collect the information from the real aspects? So we generally use the sensors. So how to connect the sensors? How we will be getting the information from the sensors, and how we will be transferring it to the cloud? That is what we require. And then from the cloud, how we will be facing it to the user side. So we are trying to demonstrate the same. I have with me the Siddharth, who is the PhD student and working under Dr. Ishad Ansari. And he delivered the initial lecture on the MATLAB also, how the MATLAB works. So Siddharth, are you there?
Yes, sir, I am there.
Okay.
I hope I am audible.
Yeah, you are audible. So I hand over the things to Siddharth, and he will be giving you the how we can connect, how the transfer can be done, and I think he will be able to demonstrate one of the examples in which we try to connect the industry through the CPS system. So Siddharth, you can take over this now.
Yes, sir. So today, in today's lab session, there would be a small demonstration of how we can actually create cyber physical systems. So in cyber physical systems, two important parts are a software side and then a hardware side. And using a network, we can connect, means network, I mean internet, we can connect these hardware with software through Wi-Fi. Also there are different devices with which we can harness the power of Wi-Fi for connecting both the device, means different domains. Now with a simple example and a very useful development board called as Node MCU, we would be uh, uh, getting to know the gist of how we can control the devices using hardware. Now please allow me to share the screen.
Siddharth, you can share the screen.
Siddharth, it is already allowed to you. So all the participants are allowed to share it.
Siddharth, are you audible?
Yeah, it is coming. No. Siddharth, I think you are muted. Yeah,
Siddharth, kindly unmute yourself. Siddharth, are we audible to you, Siddharth?
Yes, yes, sir. Yes, sir.
You are mute actually. Just
Okay. Sorry. I was on mute. So, today's session would be related to, as I told right now, today's session would be related to cyber physical system, and using a simple board called as node MCU, we can connect these hardware to actually internet. In cyber physical system, there are two important parts. First one is hardware, and other one is software. And through network, we can harness the network to connect hardware and software with each other. So there is a very simple development board called as node MCU, which we can use to connect it to internet through Wi-Fi. So Node MCU is actually a firmware which was developed to work on a chip called as ESP8266. So it was a system on chip developed by Expressive Systems, and it provided Wi-Fi facility. Now this chip could be connected to any microcontroller to provide Wi-Fi facility to it. So Node MCU people developed a firmware around this chip. Now this firmware is developed into a complete board which we can use to control different devices. So though this Node MCU firmware was originally implemented in a Lua programming language, and the whole sole purpose of this board was IoT based application development. And as I told you, initially the Node MCU name was given to the firmware, but nowadays the development board got so much popularity that it is also called as Node MCU. Now, why we should use Node MCU? So Node MCU has it in its heart this ESP8266 chip, and this chip is what is providing Wi-Fi facility to this distribution board. Now, this distribution board help in rapid prototyping. It is very easy interface, and by easy interface I mean that we can use the Arduino IDE to program a Node MCU. Actually, in starting, Node MCU used to work with Lua programming languages, but then the Arduino has a large community. Different files were developed, libraries were developed for making a Node MCU work with Arduino. So using Arduino IDE, we are having very easy interface. Now it provides Wi-Fi capability for devices, and it requires low power requirement. Now, just to demonstrate this Node MCU functionality, I need not connect it to power source. I can power this Node MCU using my USB, computer USB also. But for real life applications, computer USB cannot work because it requires large amount of current. Therefore, we would need to connect it to a power supply through different kind of step down transformer. I mean adapter. Now, but for simple applications, we can connect it to our computer USB also. Therefore, it requires a very less amount of power to work. Now, let us go through the specifications for Node MCU. So the major specification that Node MCU that we can learn from Node MCU are its operating voltage is 3.3 volts, and we can connect a 4.5 volt adapter to 10 volt adapter to it. It is having voltage regulator connected to it, so it can adapt it to the voltage that it requires, operating voltage. Now it is having one analog pin and about I think I haven't written it, 11 or more than 11 digital in-out pin. Now it is having ADC for converting analog input to digital. So this ADC is a successful approximation register type ADC, and the resolution of ADC is 10 bit. And ADC range is 0 to 3.3 volts. Now it is having flash memory as well as RAM on it. So it is having 4 MB flash memory for writing programs and 64 KB SRAM. Now, and it is having one UART, that is UART is universal receiver transmitter, SPI and I2C. All these are communication protocols. 111 means three communication protocols are there: UART, SPI and I2C. Then it provides 802.11, which is IEEE standard for Wi-Fi. It is having micro USB connector for programming the chip and providing power, and it is having digital analog input output pins. Now there are different versions of Node MCU available with us. Version 1, version 2, version 3. Now Node MCU, as I have mentioned in first slide, that it is open source. Therefore anyone can all the means connections and everything, the drawings all are present and online. Therefore anyone can create the board themselves using those. Therefore different people have developed boards, and due to this, three kinds of Arduino board versions are available with us. This is version 1, this is version 2. These both were developed by the original Node MCU guys, and this was developed by a different means manufacturer called as, this is called as Lolin, and it is called as version 3. So this is the older version, and these two are available in market. Pinouts are same in both the case. The only difference is that the USB connector protocol used by both of these Node MCU models are different. Rest is almost same. And there is one more difference in size. This Node version 3 that called as Lolin, named as Lolin, it is larger in size as compared to other MCU, Node MCU. Now we can see these are the pinout diagrams. You can see pins are labeled D0, D1, D2. So D0 means digital. So these are digital input output pins. So we are having D0, D1, D2, D3 up to D8. Digital input output pins. Then there is one analog input pin which is connected to ADC, that is A0. Then these pins are written, GPIO is written over here. GPIO stands for general purpose input output. So as the name is suggesting, it is for data input and output. Then many pins are having multiple functions. For example, we can see that some pins have written SCL, MISO, CS, and SDCLK. So these are different protocols that we saw in previous slide. That is for UART and the other protocols like I2C. So these pins are multifunctional and can be used for other purposes also. Now, before going to project, let us see an example of Arduino Node MCU project. So for the project, I would be going to an IDE. This IDE is called as Arduino IDE. IDE, those who don't know, IDE stands for Integrated Development Environment. Integrated Development Environment is actually a piece of software where we can write the code, we can compile the code, we can debug the code, and we can run the code on our the platform where we want. So we would be understanding the working of code using 2 to 3 different examples. Now, similar to Node MCU, there is one more development board which is very famous called as Arduino. So Arduino was the board which actually made a very large amount of change in this industry, means digital and circuits and all this, because it made the designing of circuit very simple. So by going through this simple program, we will first understand the working of Arduino, then we will go through Node MCU. So I will just switch on the camera and display the Arduino board that I am having with me. Then we will understand the code. This is a very simple code for just blinking the LED present on Arduino. Then we'll update a code and we'll see how can we connect more hardware to this Arduino. Then we'll go through Node MCU. So I'm just switching on the camera and stop sharing for a second. Please allow me a minute.
Siddharth, I think you are using the front camera.
Yes, sir. Virtual background is open. So I'm just stopping that virtual background.
Actually, yeah, you have to use virtual background. Then
Yes, sir. Yes, sir. Yes, sir. So the chip, I hope the screen is visible now and the camera input is visible.
yeah, slightly focus more. Actually, it is really coming. You can
Okay.
take it slightly away from the camera. So that
So this chip, the blue chip that is visible over here, it is actually Arduino chip. Arduino is again a development board. Arduino is again a development board. Uh,
Siddharth, take it slightly away from the camera because this is not really.
yes, sir. Sir, please allow me a minute.
Okay, no problem. Take your own.
So the blue chip that you can see on the screen is Arduino Nano. Arduino is also an open system, open source technology. So anyone can develop using the same specs their own chip. So people have developed different kinds of board. So this is a very small board called as Arduino Nano, and the other board, the black board that you can see on the screen is actually Node MCU development board. So we'll go through just a simple code, and this code will first blink the LED present on the Arduino, that is blue board. Then we will make changes to the board, and then this we will turn on the other LED that we would connect externally to the board. So I'll switch off the camera and I'll go to the my screen. I hope my screen is visible. So right now what you can see on my computer screen is Arduino IDE, and this is a very simple program called as blink. So this will blink the built-in LED present on Arduino. Now, first of all, we will understand the parts of this code. Then we will burn this code. The process of writing the code or the compiled code on chip is called as burning. Then we will burn this code on the Arduino. Then we can see the output. So now, first of all, what this is doing, we can see two different functions over here. First function, so in Arduino, the coding language is C. So we can see two different functions over here. The first function is called as setup. So as the name suggests, it is for initial setup. Whatever we write in code, whatever we want to do initially, we should write in this function. And other function is called as loop. So loop, as the name suggests, it is doing something continuously. Whenever we work with embedded system, we always require an infinite loop, and in that infinite loop, our functioning is we are writing our function, because in embedded system, the system is designed to read the sensor data, and at any time sensor data could come. Therefore it always works in infinite loop. So similarly, we are having two functions. First function is called as setup. In first function, we have written only one line. This line is called this line says that pin mode. Now there are different pins present on our board. So this is saying the what the function should our pin should do. So I am saying that this pin should work as output, but which pin? The LED built-in. Now LED built-in is actually a variable which is already present in the libraries. By writing LED built-in, I am telling the program that the concerned pin is actually the pin where the built-in LED, the LED which is present on the board, is connected. So in this writing, I am just setting up the initial part. So I am telling my board that the mode of that pin to which built-in LED is connected should be output mode. Now in this in other function, the function loop, what I am writing, I am actually writing the data on that pin. So first line is digital write on what pin, which the pin which through which LED is connected, and what I am saying, write high voltage to it. As soon as high voltage is written to it, LED will glow. Then what I am saying, delay for 1,000 microsecond, that is 1 second. It will wait for 1 second. Then again, what I'm writing, digital write again, write to what, same pin and as low. Now the LED which was glowing, it will stop. Then I'm again putting a delay for 3,000 millisecond, that is 3 seconds. And this is written in loop. Therefore it will keep on doing the same continuously. It will keep on doing the same. Now I am connecting my Arduino board with my PC. So as soon as I'm connecting my Arduino board with the PC, so first I have to select the port which with Arduino board is connected. So it is already selected. The board is Arduino Nano that I am having, and it is connected to some port. So right now no port is selected, but I will select COM5 because it is connected to COM5 port on my computer. We can also see this in device manager. Okay, so till the time this device manager is running, so this I can run this code. I can first of all compile this code, and I can write this code to Arduino. So in Arduino IDE, the code is called as sketch. So this is a sketch. I am verifying or compiling this sketch. This is the area where it will give me all the compile time instructions. So it is writing compiling sketch, and this progress bar can be seen. Now I can see that COM port, it is showing USB serial CH340. This is the CH340 is actually the driver for USB connection of Arduino. Now it has compiled the program. It is saying that it has compiled the program. It is using 3% of total memory. Now again, I'll go to Sketch and I upload the program to my Arduino board. So it has uploaded the program to Arduino board. Now we can see the output on our Arduino board. So I am again starting the camera. So you can see on Arduino board, one LED is already glowing and other LED is stopping and it is glowing. So it is glowing for 1 second and it is stopping for 3 seconds, as I have written in the code. So one LED is always going, it is showing the power, and other one is stopping and it is glowing. So I'll once again stop the camera and I'll make few changes in the code. Okay, now I'm making few changes in the code. So first of all, I am defining my own pin by this line hash define, by writing this line hash define LED 7. So I am saying that the 7 number pin on Arduino should be named LED. So I am naming this 7th number D7 pin as LED. Now in my setup function, I am doing pin mode LED output. That is, I am making the 7th number pin as output. Now what I am doing, when the input built-in LED is high, I am writing low to my pin number 7, to which my LED is connected. Then again 1000 millisecond delay is there. That is 1 second delay. Then again I am writing digital write high when built-in LED is low, and afterwards delay 3000 millisecond delay is there. I'm again compiling this sketch. And I'm uploading this sketch. I'll again start the camera. Is everyone able to see the screen, or should I stop the sharing screen?
It's visible, Siddharth.
Okay. Okay, thank you, sir. So now we can see the Arduino board, and I have connected this LED with my wire. This LED is connected to the D7 pin of the Arduino. Now when this green LED is glowing, the other one is stopping. When other one is glowing, this is stopping. So in this way we can program Arduino board very easy, with very easily and very simple code. Now again we will move through Node MCU, then we'll see the project description on Node MCU. Now similar code, we can work with similar code on Node MCU also. So I have made that code also. Now I will connect Node MCU with the computer. As soon as I have connected the Node MCU with computer, now in tools, the board is Arduino Nano that we selected first. Now we have to change it to Node MCU. Node MCU 1.0 ESP12E module. We have to select this firmware, and again in device manager we can see that we are having now 2 ports. COM5 was actually my Arduino, and then new COM4 is visible, then it should be node MCU. So now I am selecting port as COM4. Now this function is for blinking LED present on Arduino. Sorry, node MCU. So again, the code is same. There are two functions, setup and loop. Loop is doing same. Once it is switching on the LED, and other it is turning it off. So I'll compile the code. Now this time I am writing code on my node MCU. I'm switching on the camera, so we can see the output at node MCU. So this is node MCU. Actually, it is already having the same code. Therefore, it is blinking the LED right now. But it is compiling the code right now there on the screen. So even after writing the code, the output will be similar. So it is doing the same what we told it to do. Now you can see that the code is saying that delay should be 500 millisecond. So for half a second, it is turning it off, the LED, and half a second it is turning it on. So it is still compiling the sketch, but the output will be same. Therefore, we need not care of again uploading this sketch on our node MCU. So we'll directly move towards our presentation and see the project, a real-time project that we did for industry. So I am just switching on the camera, switching off the camera. So we did a project for industry, and the project was for implementing a device which will make the furnace present at their location compatible to industry 4.0 standard. So industry 4.0 standard says that all the devices must be connected to Wi-Fi, and they could be controlled and monitored from remote locations. So the system was actually installed to be installed in furnace. So the project was modification of existing temperature monitoring system for their industrial furnace. So in their existing system, the temperature was displayed on the digital display board, and using LED panels. Now they used simple PLC based application for displaying the temperature. The furnace had thermocouple connected to it. The thermocouple actually read the temperature from it, and PLC converted it to digital data, and it was shown on the digital LED panel. Now for making it compatible to industry 4.0, we designed a simple node MCU based circuit. Now what this circuit did, it was connected to the thermocouple. Now the output of thermocouple was in analog output. Therefore first we were required to connect this analog output to digital output, and this was connected to digital output using ADC. Now the output range was very less, therefore we didn't use onboard ADC present on node MCU, because the resolution of onboard ADC was very small. Therefore we actually used a different ADC, the industrial grade ADC, which is present in the market, and then we connected that ADC to node MCU. Now the circuit actually logged the temperature continuously on the server, and from server the temperature could be monitored from any place. You just you are just required to put the address of your server, means similar to like we say write www.google.com. Similarly we require the page address of that server, and we can see the temperature anywhere else. So this was the block diagram of that system modification. The existing system had furnace to which the sensor was connected. Sensor was, as I told you, the thermocouple, and through this thermocouple, programmable logic controller, that is PLC, was connected. So what we did, we introduced a microcontroller into this connected to sensor and PLC, and we transferred this microcontroller data to PC. So microcontroller that we used was nothing but the Node MCU development board. And how it was connected to PC, there was no wired link, it was connected through Wi-Fi. Now we can just simply have a look at the program. So I have created my own program, which is similar to the program that was used there. It is different program. I'll write that program on the Node MCU itself. Then it will transfer this content to the dummy server, and we can actually log on to that dummy server to see the output. Now in that program, we had the real sensor, that is thermocouple, which was giving us the temperature. Right now we are not having any sensor. Therefore what I am doing is I am generating random data, and this random data would be transferred to the server. So I have made my own server. There are many free services are present which provide us to create our own web page. So I have used one of that free service, and what my this Node MCU is doing, that it is reading the temperature and humidity data. Now I don't have temperature and humidity sensor right now. So what I am doing is that I am generating that temperature and humidity data randomly, and I'm transferring it to server. So first of all, I'm connecting my Node MCU to the my PC, and we will first check the output, what it is showing. Then we will go through the working of this how this is working. So first of all, I'm connecting my Node MCU. I hope I am audible. Hello, sir.
Yeah, Staj, you're audible.
Okay, so I have one more Node MCU with me. I have written the same program in this Node MCU, and as soon as I connect it to power, it will start generating the random data for humidity and temperature, and it is going to log into its web page. So just give me a second. So you can see that on the code in the loop section, what I am doing is that whenever this loop function is starting, I am doing digital LED low, digital write low on built-in LED. So LED will turn off. As soon as it is doing everything to means transfer the data to the server, after that I am doing digital LED, digital write on LED high. So after doing everything, it will turn on the LED. So I'm turning on the camera to see the same thing. So as you can see, this is a Node MCU on which the same code is running. Now LED is stopping. It is saying that it means that it has started in that void loop function, and it has done transferred data to the server, and again LED is glowing. It means that transfer is complete. So we can see what it is transferring to the that server on our computer also. So let us see which port this board is connected. It is connected to COM3. So I'm right again doing port as point, selecting port as COM3, and there is a tool called as serial monitor. So in serial monitor, we can see what our Arduino is doing. So it is showing that it is connected to Wi-Fi, and its IP address, that is local address is this, and this is the temperature. It is which it has generated. It is not the real temperature. It has generated it randomly 28 degrees Celsius, and humidity is 81 degrees Celsius. Sorry, 81%, and it is now transferring this to server. So whenever you are seeing waiting, so it means that it is waiting for the server transfer to complete. Now there is a server that I have made, so we can go through that server and see the code over there. So this is the server page. Sorry, I made a mistake. uh, I hope my screen is visible. So you can see it is logging all the data to the server. So today's date is 12. It is logging it with the time. So today's date is 12, and right now time is 5:12:56. 5 means right now it is 12:56 p.m., and it is showing us the temperature. So this is the server page that I have created. So what Arduino is doing, node MCU is doing is it is generating that data, and it is transferring to my this server, and logging the data to here. Now using different tools present on server, we can either clear the data. So it will clear all the table data, so we can see only the recent data over here, and we can also download the previous data, that is logs. So we will go through very quickly, go through the code on Arduino, and then we will go through the simple code on the server side. So I'll not go deep into this code. I'll explain it very in brief. So first of all, in this code, we are using certain header files. These header files are required to provide the our node MCU with the capability of connecting to Wi-Fi server. So what I am doing is, in first function, that is initial function, setup function, I am telling it that make the built-in LED as output pin. Then the serial begin is for logging the data onto the art's own system that we saw in serial monitor. Then I am here connecting it to my Wi-Fi. I have provided it my Wi-Fi password and the name of my Wi-Fi. And after connecting it, it will give me the if it is connected correctly, successfully, it will give say tell me that it is connected, and it will give me IP address. And this is the only work of setup function. It will run only once. Now in our loop function, what I am doing is I am generating random data as temperature and humidity. Now in whenever in real time case, we had actually our sensors which were generating temperature data and humidity data, but that data was generated using means in analog form. So we had one more piece of code which was for controlling the ADC, that is analog to digital converter. Now this analog to digital converter converted this analog data, temperature and humidity data, into digital data. Then we pass this data to the server. Now it is creating a post request for the server, and in this post request, it is actually inserting all the data that we are creating over here. And after this post request is created, it is printing this request to the server. And whenever whenever this request is means connected, we are connected to the server, we will stop the request, and the thing will loop on continuously. So we are creating the our post request over here. As soon as post request is done, it will stop the connection. Again, it will do the same. So there is we are putting two delays over here. One delay is for 1000 millisecond, that is 1 second. Then again there is one more delay that is for 3000 millisecond, that is 3 second. So total 4 second delays are there in between consecutive post request that we are making to server. And including latency, the delay is around 5 seconds. So what we are doing in the server side, so this is the server side code. So in server, a simple PHP script is running. PHP is a well-known program for writing server side code. So in PHP script, what I am doing, first of all, it is just Arduino, Node MCU is not providing any time data. It is only providing temperature and humidity data. So we are first of all, we are generating time data. So we are pulling the time from server itself. First, we are saying that the default time zone should be of India, that is Asia and Kolkata. Then we are generating time in this format, that is day, month and year, and hours, minutes and seconds. Now whenever we are creating post request, we are using two variables. One variable is temp, other is humidity with capital H. You can see the same variables present over here also. Two variables are there, humidity with capital H, and other one was temp. So these variables are actually recognized at our server. So we are making a post request. Therefore, I am using this function which is present in PHP. That is, it is identifying this post request. As soon as this post request is made, the temperature data will go to this variable name as temp f, and humidity will go to this another variable hum. And we are creating two log files. One is for historical data. So I am going to write all the temperature humidity data along with the date in this log file. And similarly, there is one file that is called as tables. It is the file which is showing the data on the screen. So this is how this system is working. So even you can also do it from your side if you want to see the working of this program. So you can just type this address into your screen, into your browser, and you can see the same output at your screen also. But only problem is that this whole system was made to be controlled from a single end. Therefore, this clear data is actually will clear the data from everyone's screen. So this is not a client side button, but this is a server side operation, what it is doing. So means I request you, if you want, you can type this address in your screens also, in your browsers also. The address is myesp8266.webpages.com/test/index.html, and you can see the same. It is generating all the temperature at my end, and you can see it from your end also. So we can see it on serial monitor also. In serial monitor, the current address, current temperature was 12 and humidity was 73, and on the screen it is same 12, and it is only showing temperature data. Therefore, we can see 12 over here. So this was the project, and this is how we can implement a sensor based system using Node MCU. So this was from my side. If there are any question, we can talk about them also. We can discuss them.
So, people, any question? How does Siddharth has gone through? You can just ask anything.
If there are any question related to the working of server or Node MCU, we can see those questions. So last thing which I would like to add here is that the Node MCU, that this development board can work in two configurations. In one configuration, it can work as server. In other configuration, it can work as client. And whenever it is working as client, it is going to send data to the server. So right now, the configuration that we discussed through this project, in this configuration, it was working as client and it was sending the data to the server with web address present on the screen, this web address. So in other applications, what we can do, we can create node MCU as server, and using our own mobile phones or using our laptops, we can actually log on to our node MCU also. But using node MCU as a server means it is having very less computation power, therefore it cannot handle large amount of traffic, but it can be used for means some hobbies project or prototyping, or just means testing our means any proof of concept thing, we can use that also. So this was from my side.
Yeah. Any question?
Hello.
Yeah. Any questions? Anything? Participants?
Yes.
Question, participants are in hybrid.
Want to know the machine learning?
Yeah, please continue with your question.
Sir, if it is a machine learning and we want to predict this future data, are we writing the code in the Arduino programming?
Sir, machine learning requires very large amount of means computation power. So we actually cannot use means Arduino or Node MCU for machine learning. We will require means a better board. For example, we can use Raspberry Pi. Even in Raspberry Pi, we cannot actually build the means train our model. We can train the model at somewhere else, and we can use them on Raspberry Pi. So we can use machine learning application, but when they are present on server side, in that case we can, if our machine learning application is working on server side, then we can use our Arduino or Node MCU to connect to that machine learning application, but we cannot run any application on Arduino or Node MCU. I hope I am clear.
Yes, it does. Thank you.
Thank you, sir. So this was all from my side. Please allow me to stop sharing.
Any other questions for any of the participants? Any other participants?
Okay, sir. So should I leave the meeting, sir, if there are no questions?
Yeah, it seems. From the participants.
If there's no question, we can thank Siddharth. Siddharth, you can be present and we can take a group photograph.
Okay, sir.
Switch on your camera. All of you, please switch on your camera.
Actually, sir, my camera, I'm having using handheld webcam, so it would be difficult.
No issues. Whatever is convenient to you. Swati and Mandoi, Mithilesh. Okay, so all set. I think tomorrow we are going to wind up this program. So you can smile now. So just give a big smile so that we can record it. I'll be equally happy that went smoothly and successfully. Okay, So just one last reminder, tomorrow, apart from 2 lectures of Professor Imre Howard, you have to appear in the quiz at 4:30. So we'll share the quiz probably 5 minutes before the time over email. It will be a PDF file. You can write on the PDF file, you can convert it to Word file, or you can handle it in small questions, whatever best you can find, you can do it. And we have to submit by 5:30. It will be really short, just I think 6 to 10 questions in between, something like that. Just a general understanding of what you have gained from the course, basically the outcome of the course that you have got. Okay, any question from your side?
No, sir.
Okay, if no question, let's close everything.